Hey guys, today we're going to solve LeetCode number 980, unique path 3. So we're given a grid with 4 types of squares. If the value is 1, that's the starting square. If the value is 2, that's the ending square. If the value is 0, that's a traversable square, so it's an empty square that we can walk over. And -1 are the obstacles, so we cannot walk over those cells. And what we need to return is the number of 4 directional walks, so the paths that start from the starting square and end in the ending square, and they need to walk over every empty square exactly once. Okay, so one key insight is that from this, like, we know that we need to walk on every empty cell only once, and so essentially after we've walked on one empty cell, we can set that cell to be kind of the same as an obstacle. Like, we don't want to walk on it again, so we're going to have to treat it exactly as an obstacle cell. Okay, so the way we're going to do this is we're going to basically brute force our way through. And so, as you know, I like to do at the start of these problems is define the directions in which I can move. So these are the usual directions. And then what we're going to do is we're going to store some variables. So here we have the result. This is going to be our return value. And this is the amount of cells that we know are currently traversable. And you're going to see why I'm setting it to 1 later on. It's going to make our depth-first search function really easier and more readable. So then we need the starting x coordinate and the starting y coordinate, or the starting row and the starting column. Doesn't matter how you call them. And now we're also going to need the number of rows in our grid, which we call m, and the number of columns in our grid, which we call n. Okay, so now what we're going to do is we're going to loop through all cells in our grid, and we're going to check if they are traversable. And if they are traversable, then we're going to increment this variable. Okay, so just loop through all rows, loop through all columns, check if the current grid is traversable, and if it is, increment the traversable variable. But if it is not traversable, then maybe it is the starting position, right? And so in that case, we need to update our variables that keep track of the starting position. Okay, and now we have the amount of traversable squares and we have the starting position. So we can now call a depth first search function that starts from our starting x and y positions and checks all of the possible paths to go to the cell to the ending square. And after calling this function inside will increment our result. So we are going to be able to return the result. Okay, so now all that's left is to implement the depth first search function. So to implement this, we're going to take 2 parameters, the row and the column. And now what we're going to do is we're going to check if we are out of bounds or if we are on an obstacle. So if we are out of bounds on the rows or on the columns, just return. And the other condition that will make us stop our depth first search is if the current cell is in the bounds of the grid, but it is less than 0, meaning that it is an obstacle. Okay, so in those cases, we can just return. So we want to end our depth first search. And now what we can do is we can check if the current cell is actually the ending square. And if the current cell is the ending square, then we want to increment the result by 1 if we have walked on every non-obstacle square once. So if we basically consumed all of the traversable squares, we can increment the result by 1. Okay, so if there are no more traversable squares, increment the result by 1. And so why are we doing this? It's because now you're going to see that at every step, we decrement the traversable steps by 1. Because when we do a depth first search on this row and column, we consider this cell to be traversed. So what we want to do is we want to set it to a negative value so that we won't walk on it again. And we want to say that now we have 1 less traversable square. So essentially, we're setting this to be kind of like an obstacle, right? It's kind of the same thing as an obstacle. And so after setting the grid to a negative value so that we won't walk on it again, and after decrementing the traversable count, we can start our actual depth first search, meaning that we can take our directions and do a for loop on those. So this is the delta row and the delta column. And now we want to call the same function on the current row plus the delta row and on the current column plus the delta column. Okay, and so yeah, that's it. Now we're just going to have to set our cell state to the original state, which is definitely traversable, or I mean, it could be starting, but we don't really care about that. So yeah, we want to set it to the original state or equivalent state and increment back the traversable because we decremented it. So we don't want to leave it dirty. We want to restore this to be the previous value. Okay, so that's it. I'm going to show you that it works. And this is actually a solution inspired by Lee 215. He's a great competitive programmer. So yeah, it's an O of n to the power of 3 time complexity solution. And the reason for that is that for any grid cell, you're going to start another depth first search function, essentially just on 3 neighbors, because the previous neighbor is going to have set to -2, and so here it's going to return. So we're not actually starting a depth first search on 4 elements. We're only starting it on 3 elements.